Today we're talking Jensen. Okay guys, so the Jensen's inequality states that whenever we have a concave function f, then that function evaluated at an average of some n arguments is greater than or equal to the average of function values for that function for that argument evaluated separately, and the opposite when f of x is convex. Okay, so, well, two questions. What the hell does it mean for a function to be concave or convex? And second of all, what the hell? What's happening here? Okay, so we'll address both of those questions separately. Okay, so what does it mean for a function to be concave? Well, it means for it to curve kind of upwards, yeah? So let me draw the coordinate system here, the y and the x-axis, and let me draw the square root function. We can see that this function curves kind of upwards, yeah? So this curvy, shape goes up, like, in a sad face, for example, yeah? Like it was a mouth of a sad face. However, a convex function, on the other hand, looks a little bit differently. So it will curve kind of downwards, for example, like the x squared function. Yeah, so it will look more like a smiley face, yeah, if you were to draw some eyes to it. And how are we supposed to know whether a function is concave or convex just looking at the formula describing it, not necessarily looking at its graph? Well, let me for now erase the function x squared from it, and let's just examine the square root of x. Yeah, so if you see, if I draw now the derivative of this function, the tangent line to the curve, at some argument, let's say x naught right here, and then I go on and draw one more tangent line to the curve, one more derivative at some other point, let's say this time at the point x equal to 1. Well, we see that the tangent line at the point x, not x equal to 1, but x sub 1, at x sub 1 will have a smaller slope, yeah? This one is actually, yeah, this is less steep than the line tangent at the point x naught. So we said as the x's are increasing, the slope of the tangent line to the curve decreases. Well, it means that the rate of change of the derivative, which is the rate of change of the function itself, is negative, and so the second derivative of the function is negative. So what we get is that whenever the second derivative of the function is less than 0, then f is concave. However, if a function is convex, so let me draw one more coordinate system right now, yeah, so that's once again my y and my x-axis, and now I draw, let's say that x squared function I was talking about earlier, yeah? So now when I draw a tangent line, I wanted to do this in yellow, one more tangent line to this curve, yeah, for example here at the point x naught, right there, x naught, and then I will draw one more tangent line, let's say at the point x sub 1 right over here, then we can see that the slope of the tangent line increases as we go along the x-axis in the positive x direction. And so what we see is that the rate of change at which the derivative changes is positive. And so, well, the rate of change of the function itself is positive, which implies that the second derivative of the function given is actually positive. And so we see that the second derivative of the function being positive will imply the function being convex. Okay guys, so once again to the inequality itself, what does it even state? I mean, how are we supposed to understand all of those with sigma signs, those f of x's and x sub k's? It's just too much of it, yeah? So let me simplify the case for only two arguments, x1 and x2, yeah? So I would like to now draw myself some kind of a convex function, yeah? So it will look, I don't know, something like this, yeah? So it will just nicely curve, upwards, not downwards, yeah? It will just nicely curve upwards. It will have a negative second derivative, all of that kind of stuff, yeah? So now if I choose myself two arguments, let's say some kind of an x1, I want to do this in yellow, yeah? So some kind of an x1 and some x sub 2 right there, yeah? And I evaluate the function at those two variables, at those two arguments, I'm gonna get two separate function values, yeah? So here I'm gonna get the f of x sub 1, here I'm gonna get f of x sub 2 like this. But now, because my function is concave, I can do any trick there. You see, I would like to evaluate the function at the arithmetic mean, yeah? So at the average of those two arguments I already evaluated that, yeah? So I just, well, evaluated in the exact geometric middle of this segment between x1 and x2, yeah? So at x1 plus x2 all over 2. And now when I evaluate the function at this exact point, I will get my, well, the function value for the average of those points. But now, if I take the average of the function values for those arguments evaluated separately themselves, and I draw it somewhere here, yeah, so I will connect them with a line segment, for example. Oh, it didn't work, yeah, so I would like to connect those two with a line segment, and now I would like to take the middle of the line segment right here, and then this, it's here, yeah, then this is gonna be the average of those function values evaluated separately, yeah? So we see that the function evaluated at the average of those arguments is greater, yeah, because it's higher on the graph than the average of the function values when we evaluate this function at those arguments separately. And just about the opposite thing happens for f that is a convex function. So if I were to draw myself a coordinate system, yeah, once again with my lovely y and x axis, now I would like to draw some kind of a convex function, then if I were to mark some two arguments, yeah, x1 and my x2, and calculate the function value for those two arguments here and here, then I would get that after evaluating the function here at the arithmetic mean of those two arguments, I will end up, let's say here, yeah, then this is actually less than the average of the function values of that function for those arguments evaluated separately. Because now if I were to draw a line segment connecting those two points on the graph given by those arguments, yeah, the average, the middle, the middle, no, this is not quite a middle, but it's somewhere here, I guess. Yeah, this guy wasn't perfectly straight, should have been like a little bit more to the left, but nobody cares about it yet. So we see right now that this point right there is the average of the function values evaluated at those arguments separately, and this is higher on the graph, it is higher on the graph than the function evaluated in the average of those two arguments. So how do we prove the Jensen's inequality? Well, I would like to do this one by induction. However, well, I would like to only cover the proof for the concave case because, well, when f is convex, it's just the same proof, but kind of the other way around. So maybe I'll leave it as an exercise for you guys. Yeah. So how are we supposed to prove Jensen's inequality by induction for the case of f being a concave function? Well, the first thing we'll have to do is prove the base case. Well, a base case being 1 doesn't really make any sense, because it would mean that we are trying to get the inequality for only one argument. Doesn't really make sense, but for 2 arguments, well, now it makes some sense. So let's maybe go back to our curve, and let's say that we would like to now achieve the base, that we would like to achieve the base case. Well, I kind of gave you guys the graphical proof of the base case already. However, well, there is also a formal proof of the base case. It's called the Lagrange theorem. That kind of implies the statement here, though it's not explicitly the base case for this proof. It means that for whatever secant line that goes through it stays that for whatever secant line that goes through some curve, yeah, so there's a secant line that goes through a curve, we are able, on the interval between the x's, x1 and x2, that give us the points at which that secant intersects with the curve, that on this interval somewhere here we can find a place, we can find a point on the curve such that the tangent line at that point is exactly parallel to that secant line. And well, as we know, it will definitely imply our statement, as our function is just about always above our secant line, yeah? So, well, that kind of implies the statement, and now we can just move to the induction hypothesis, yeah? So we'd like to, right now, make the assumption, yeah? So, assumption. We would like to assume that our statement, so our Jensen's inequality, will hold for n. And I would like to actually prove the more general form of the Jensen's inequality. So instead of proving that the function evaluated at an average of some variables, yeah, of some arguments, is greater than or equal to the average of function values for those arguments separately, I would like to prove that whenever we have a function evaluated at a sum of some arguments multiplied by some weights, then it's going to be greater than or equal to the sum of the function values of those arguments multiplied by those weights whenever the sum of all of those weights is equal to a 1, and well definitely f is concave, yeah? So this is gonna be my hypothesis, yeah, hypothesis that for some given n it will actually work out. And I would like to conduct my proof with the inductive step, and I actually have to do a little bit more space here, so let me just move this base case to the left hand side of the screen, and I would also like to move the assumption to the left hand side of the screen also. And now, how are we supposed to do it? Let's first of all rewrite it, or maybe I will first of all write down the inductive step, yeah, just for the sake of consistency. Let's first of all rewrite our problem in terms of n, well, becoming n plus 1, yeah? So what we'll get is just f evaluated at the sum from k equal to 1 up to n plus 1 of a k multiplied by xk. Well, how can we rewrite this thing, also knowing, by the way, that the sum of all of those n's, all those a's is equal to a 1, and oh yeah, I should have put a n here, lovely. So how can we rewrite this thing? I mean, we would like to get an n in the subscript for sure, because maybe then we would be able to get, this inductive step to a position where it at least resembles the stuff we had in the assumptions. So let's try and do it. We would like to get rid of this n plus 1 in the subscript. So what do we have to do in order to achieve this? Well, we have to just take out the n plus first term of that sum. So we'll have the sum from k equal to 1 up to n of a k x k, and then we just have to add that a sub that a sub n plus 1 x sub n plus 1. Lovely, but now the problem is that we once again can't really use our how to say it, man, our inductive hypothesis, because now those weights here don't really sum up to a 1, because now those weights here in the sum are, well, a1 through ak, but they sum only to 1 minus a sub n plus 1, up to an, but they sum only to 1 minus an plus 1. So well, what can we do about it? Well, actually, we can do quite a lot about it. We'll just go on and kind of factor 1 minus an plus 1 from that sum, and then we'll be left with the sum as k goes from 1 up to n of ak divided by 1 minus an plus 1, yeah, times x k, and then we have to add that remaining an plus 1 x n plus 1. Yeah, so now, as you can see, the sum of all of those weights here is just a1 over 1 minus an plus 1 up to an over 1 minus an plus 1. So that's just going to be 1 minus an plus 1 over 1 minus an plus 1, which is 1. Awesome. But now, well, I see one more nice thing. You see, the sum of this 1 minus an plus 1 and an plus 1 itself, there's just a 1. And so we could use the base case scenario here. We could use the base case for n being equal to 2 here. Just, well, kind of considering this guy, kind of interpreting this entire sum as a single constant, as a single argument, yeah? So, well, let's go on and do it. We will get that this is actually going to be greater than or equal to by our inductive base case, than 1 minus an plus 1 multiplied by the function, so the weight multiplied by the function evaluated at the sum of those arguments, yeah, so well, basically just an argument, because that's how we chose to treat it, x sub k, and then plus a sub n plus 1 multiplied by f evaluated at x sub n plus 1, not k, bro. Yeah, now it's awesome, because, well, the only thing we have left to kind of deal with is f evaluated at the sum from k being equal to 1 up to n of ak by 1 minus an plus 1 times xk. But, well, we could, without a problem, just use our inductive assumption here. No, man, the inductive assumption here, and that's because those weights sum up to a 1. Yo, awesome. So let's go on and do it. Then we'll be able to say that this entire thing is just is greater than or equal to, once again, is greater than or equal to 1 minus an plus 1 multiplied by, and now it's going to be the sum as k goes from 1 up to n of a sub k all over 1 minus n plus 1 of the function evaluated at x sub k, and then plus an plus 1 f of x sub k. But now the nice thing is that, well, this stuff right here is not inside of the function anymore, so we can just go on and multiply it through by 1 minus an plus 1, getting rid of that awfully looking fraction inside of it. So just kind of getting everything into order, we will get the sum as k goes from 1 up to infinity of ak f of x k plus, and then we have this remaining an plus 1 plus, sorry, not plus, but multiplied by f sub x n plus 1. I'm not good with those goddamn subscripts. But now we can, without the problem, just go on and suck this thing into this sum itself. And what we'll end up with after all of this tedious calculation is k equal to 1 up to n plus 1 up to n plus 1 of ak f of x sub k. And, well, this is actually exactly what we wanted to prove, because we got that, well, f evaluated at that sum of all those arguments multiplied by those weights is greater than or equal to the sum of all of those functions evaluated at those arguments times those weights which is awesome. And if you wanted to conduct this proof for the convex function, you just kind of start here and, well, walk your way, you know, upwards in kind of the opposite direction, yeah? Lovely. Let's go to the problems. And one more caveat, guys. So we proved the Jensen's inequality for some ways that sum up to a 1. And so why does it even imply the statement that I showed you guys at the very beginning of this problem? Yeah, so the statement with all of those, you know, averages and stuff like this. You see, what I'm doing here is I'm assigning every single one of those arguments a weight of 1 over n. And, well, since I have n of those variables, well, the sum of all of those 1 over n's and times is just going to be equal to nicely a 1. So there is absolutely no problem in doing that. Okay, guys, so for the first problem, we would like to prove the AMG inequality. Well, that's interesting. You see, the AMG inequality stated that, if you don't remember it, that the arithmetic mean, yeah, so the sum of some numbers divided by the amount of them, yeah, is greater than or equal to the geometric mean of those numbers, which is, well, just the nth root of the product. Well, what does the Jensen's inequality state on the other hand? Yeah, so that was the AMGM. Now the Jensen. What does the Jensen state? Well, it states that if we have a function and we evaluate it at a lovely average of some n numbers, it's going to be greater than or equal to the average of the function values for those arguments evaluated separately for a concave function f, yeah? Okay, well, this is quite interesting because as you can see here we've got, you know, this arithmetic mean, this here we also have this arithmetic mean, it's, you know, kind of similar. So maybe we could use the Jensen's inequality to prove the AMG inequality, yeah? The only problem is that here we have some addition on the right hand side, and here we have some multiplication and some, you know, n fruits, we have dividing by n, here we have n fruit on the right hand side. So, well, I think we will have to choose a right function that will connect addition to multiplication and dividing by n to taking the nth root. And there actually is a function like this, which is also concave, which is the natural log of x, f of x being equal to natural log of x, because, well, the sum of natural logs is just the natural log of the product of those numbers, and, well, if we divide the log by n, is the same as taking the log of x to the power of 1 over n. Well, that's awesome. So let's just go on and plug this thing into here. So what we'll get is the natural log of x1 all the way up to xn all over n is supposed to be greater than or equal to the natural log of x1 plus all the way up to natural log of x sub n all over n right now. And so we'll just focus on the right hand side of this inequality. What we'll get here is just the natural log of the product of all, of the product of all of those n's divided by an n. But that's just equal to the natural log of the nth root of the product of all of those numbers. And now just, you know, without the problem, raise e to the power of, well, every single thing we have here in this chain of inequalities and equalities. And so what you'll end up with is that x1 all the way up to xn all over n is greater than or equal to the nth root of x1 all the way up to xn multiplied together, which is the desired AMG inequality. Okay, guys, so problem numero dos. So we are supposed to prove that for all triangles ABC, sine of A plus sine of B plus sine of C is less than or equal to 3 square roots of 3 all over 2. Well, sine of A just means the sine of the angle next to the vertex A, if you didn't catch it already. Yeah. So how are we supposed to do it? Well, once again, as always, when we're trying to solve something about Jensen's inequality, we just have to, well, find a nice function that we can, you know, plug into our inequality. What is a function we could use now? Well, we are given this sine all over the place in this problem, so maybe the sine would be a nice thing. Well, is sine convex or concave? Well, some of you might think, well, bro, this is a stupid question, because sine looks, well, something like this. It's a wave, it curves upwards and then it curves downwards. Why are you such an idiot? Why are you trying to figure out where it's concave or convex, yeah? Well, actually, there is a deep sense to it. You see, those angles, A, B, and C, are angles that are inside of a triangle, yeah? And so none of those angles can be greater than 180 degrees, and none of them can be less than 0. And so we see that A, B, and C are all in the interval between 0 and 180 degrees, yeah? 0 degrees and 180 degrees. And it's lovely because, well, what is sine between 0 and pi over 2? And pi? Well, it's positive as hell, so we can just kind of go on and say that it's gonna be, well, convex or concave on that particular interval, because it does not change its concavity on that interval between 0 and pi. Okay, so what is that, sine between 0 and pi? Well, yeah, we know that it's gonna be, well, concave because it just curves upwards if you know the graph. But, well, if you wanted to check it, the d squared over d x squared, so the second derivative of sine of x is just equal to negative sine of x. So yeah, if sine is positive at that interval, on that interval, then negative sine is going to be negative. Oh man, I have such a sore throat. I've been recording for, I don't know, like 3.5 hours today. And it's gonna be negative sine of x. Awesome. And so, well, we see that sine is just going to be concave because its second derivative is going to be negative on that interval. Awesome. So now we can apply the Jensen's inequality to this thing. We are looking for an upper bound, for an upper bound of those sine of A, sine of B, and sine of C. We can get it by Jensen. It's going to be sine of A plus sine of B plus sine of C is going to be less than or equal to what? Well, if I were to divide all this by 3, so take the average of those fraction values, it would be less than or equal to just a huge sine of the sum of A, B, and C all over 3. But, well, that's pretty lovely because we know A, B, and C are angles inside of a triangle, so their sum is gonna be equal. It's not supposed to be a D, it's supposed to be a B. Oh, now it's better. It's supposed to be 180 degrees. And so this thing is going to be equal to the sine of 60, which is a square root of 3 all over 2. And now we can just go on and multiply everything through by 3, getting that 3 square roots of 3 all over 2 is greater than or equal to sine A plus sine B plus sine C. Lovely. That will be all for the problem. Let's go further. Okay guys, so for the third problem, we would like to prove that for all triangles A, B, C, the cosine of A times cosine of B times cosine of C is less than or equal to 1 over 8. Awesome. So how are we supposed to do it? Well, the only problem is that we're not really adding stuff together. We are multiplying those sines, those cosines, yeah? And so directly applying Jensen's not gonna be possible. But I'm think maybe you could use the AMG inequality here. I see some kind of a probability that it would be a nice idea to do it. Rewriting this inequality will give us that 8 cosine of A times cosine of B times cosine of C is supposed to be less than or equal to 1. This is exactly what we would like to prove now. But now we can get an upper bound, maybe not exactly 1, but some kind of an upper bound for that product of cosines using the AMG inequality. We can actually get that this product is going to be less than or equal to double cosine of A plus double cosine of B plus double cosine of C, yeah, everything nicely by 3 and everything to the power of 3 as well. So now we just have to prove that this thing is going to be less than or equal to 1. So let's get rolling. Let's do it, yeah? So we would like to prove that this inequality here holds. How are we supposed to do it? First of all, we can just, go on and nicely take the cube root of both sides. We don't really care about it. I mean, 1 is the 1, yes? So we only care We can also, multiply everything through by a 3 and divide everything through by a 2. So we would like to prove that cosine of A plus cosine of B plus cosine of C is less than or equal to 3 over 2. But now, well, we can use Jensen. Cosine on the interval between 0 and 180 degrees, because this is the only interval that we care about, is a concave function, so there's no problem for us to just say that this guy right here is going to be less than or equal to cosine, actually 3 multiplied by cosine of the sum of our angles all over 3. But the nice thing is that the sum of those angles is going to be just 180 degrees. And so this stuff is going to be equal to a 60 degree. And so cosine of 60 is equal to a half. So this thing's going to be equal to 3 over 2. And so if 3 over 2 is greater than or equal to the sum of those cosines, well, then the double sum of those cosines by 3 all to the power of a 3 is going to be less than or equal to a 1. And this will mean that A times cosine of A, cosine of B, cosine of C is going to be less than or equal to a 1. Perfect. Let's go forward. Okay guys, so for the last problem, we would like to solve something more Olympiad level. So we are given 3 positive real numbers, A, B and C, such that the sum is equal to the product, and we are supposed to prove that 1 over 1 plus AB plus 1 over 1 plus BC plus 1 over 1 plus CA is less than or equal to 3/4. Lovely. Oh, how am I supposed to do it? Well, we are supposed to do this one by Jensen, as you probably have already guessed. In my country, we pronounce it Jensen, so don't kill me for it. Yeah. So we'll have to probably find some kind of a function that will, I don't know, maybe resemble those reciprocals, those fractions a little bit. But first of all, let's try to rewrite this entire thing, do it a little bit more, function-like, because let's be just honest here, those fractions, they don't look like functions. I mean, what this kind of fraction like this one would be a function of A times B? Like, would I be supposed to make a function of 2 variables, like f of A and B equal to 1 over 1 plus A times B? Well, not quite. I mean, we don't have a Jensen inequality for stuff like this. But I can manipulate this expression, for example, changing this 1 over 1 plus AB into A over A plus ABC. I'm not changing anything, I'm just multiplying through the denominator and the numerator by A. Then I can change this guy into B over B plus ABC, and the last guy here into C over C plus ABC. Pretty lovely, yeah? And well, this thing's gonna be supposedly less than or equal to 3/4. But now it makes a little bit more sense. Now I can just kind of go on and take myself a function f of x equal to x over x plus a, b, c. And well, for positive real a, b, c, this guy is gonna be a concave function. So, well, you just have to kind of trust me, because calculating its derivative is gonna be tedious as hell. So, well, I just leave it as an exercise for you guys to practice your derivatives a little bit, yeah? And so it will mean that we will be able to say that this A over A plus ABC plus B over B plus ABC plus C over C plus ABC is going to be less than or equal to, well, A plus B plus C, I mean, triple the value of the function and the stuff, so A plus B plus C over A plus B plus C. I should have said A plus B plus C all over 3 over A plus B plus C all over 3 and plus A times B times C. But now, well, we recall that A, B, C was equal to A plus B plus C pretty nicely. And so we will get it's going to be all equal to, well, 3 multiplied by A, B, C all over 3 all over A, B, C all over 3 and then plus A, B, C, which is equal to, guess what, 3/4. Lovely. So what do we do here? Well, we just kind of got ourselves a function of x equal to x over x plus abc. After, well, noticing that this guy is going to be concave, we were able to finish out this problem within seconds. I just love Jensen. It's an awesome inequality. Okay guys, so I really hope you enjoyed this video. If you did, then well, like and subscribe to my channel, because then you will not miss out on anything I'm gonna be posting in the future. And I post every single day, and actually sometimes 2 times a day, so twice a day. So well, just you should know that there is a lot of stuff to miss out on. So well, subscribing to me is a nice thing to do. Yeah, anyway, if you like this video, well, I'm happy, you're happy, everyone's happy, and see you in the next one. Bye.